Have you ever wondered how we can match between multiple images? For example, when we remember that a particular part of the city looks like a part of a different city, how do we actually do that? How can we use a similar concept to estimate depth with two different views from each of the eyes? In today's episode, we will demystify the world of corners. First, let's consider a stereo camera setup just like the ones we have. We have eyes which are side by side, and we have two of them. So imagine you have two different cameras which are placed side by side for giving our robots a stereo vision system. Now let us say the distance between the two camera centers is called the baseline P. So this baseline is like the interocular distance, or the distance between the two eyes, and which is different from person to person, and that's what is used in the opticians clinic when they try to measure what kind of spectacles would fit for you, right? So these two cameras basically see the world from a slightly different viewpoint. Let's say we want to now identify the same part of the image in both the images. So let's say we want to do this manually first, and I will pick a arbitrarily important or prominent part of the image, which in my case, I like the mountain top with the snow. So I'm going to just pick that. So I'm going to label them as the red color for the left side camera and the blue color for the right hand side camera. So if we color code the entire image, this is what it would look like. So just to show you the fact that this actually gives you a different viewpoint, I'm going to overlay these two images. Right? As you clearly see, they're definitely not the same images, but they have similar sort of context or content in them. Right? Let's zoom into this image, and if we are able to measure how far apart these points are in pixel units, we will call this the disparity D. And we can essentially compute how far something is. So depth is computed as focal length, which is known for the camera because we picked the lens for the camera, into the baseline, which is the distance between the two cameras, or the interocular distance, divided by the disparity, which we just computed by clicking the same point in the two different views. So which is Z is equal to F into B divided by D. A similar exact concept is used for stitching panoramas in your phone. We do the same idea. We basically can click on the same points and estimate how much the image has moved, and essentially add the other parts which were outside with the same transformation, right? The question is, in the previous case, I as a human being picked what was a good feature, right? How do we make a computer do the same thing? To answer that question, we need to first ask a very philosophical question. What point do we pick? What makes a good feature? What is a good image point in this case, right? So let's take an arbitrary sample here, right? I'm gonna pick a point on the sky. Sky is beautiful, sky is important, right? Sky is big, it's vast. The question is, in this particular part of the image, the sky is just almost plain white, right? And it looks exactly the same as any of these 3 points on the blue colored image, which is your right hand side image. Okay, that's case number 1, right? Which is kind of not a good thing because you don't know the exact correspondence between the left image and the right image, because a point on the left image corresponded to multiple points on the right image, and it's very hard for us to know which is correct here, right? Okay, let's take another example. Let's take a different point, the blue color point in this case. I'm going to pick it on the vertical rays of the sun, right? If I try to match it, it will match again to a few points, but it will be much fewer because it's going to be on the same exact line, right? In the previous case, in the red color point case, it could match all over the sky, which is a lot of large area, which is bad. In the blue point case, it's constrained to that ray of the sun, so which is a much smaller place, which is great. And if I pick the mountaintop, which is with the snow which we picked before, the green point, it's going to match only one single point. Okay, this is beautiful. This is great. If I write a computational algorithm, the green point is going to have a unique solution. The blue point is going to have a finite number of solutions which are relatively small, and the red point is going to have a finite number of solutions as well, but it's going to be a large number, which is bad. So essentially, if we are talking this in computer vision terms, the red color points correspond to flat points. Flat here means that there is no change in intensity as you move left or right of that pixel or up and down of that pixel, right? So there is very little change in all directions, which is bad. So the blue color point lied on or what we call an edge, which means that there is no change along the direction of the edge, but normal to the direction of the edge or any other direction, it would basically be a significant amount of change. So if you pick the green point, that lied on what is called a corner, right? So it's the same ideology as the corner of a table. There is significant changes in all the directions. If you have not watched the lecture on edge, now is the time to go watch it, where I explain the intuitive idea of how we can actually come up with a metric or a mathematical toolkit for finding an edge. We are going to utilize the same concept today, but we are going to apply that a few times to use that to find a corner. So now we want to detect change. This is a quick recap. So let's pick the same point from before. And we want to say that, hey, like, let's look at the change in both X and Y direction, which is horizontal and vertical, right? This is going to be given to us by the gradient in the X and Y direction respectively. And the intensity change essentially is given by the numerical derivative, which is the term of I of X plus U, Y of comma Y plus V minus IXY, where the point is centered around XY, and IX plus U and Y plus V is basically the shift, like a different point which is like close by, and like we are trying to find how much is the difference, which is essentially the gradient change. And this function W is the window function or the smoothing function to reduce noise, because when you take an image from a camera sensor, as we have talked about in the previous episode, it is noisy, especially if you take images at high ISO or something which is like zoomed in because of the air turbulence. So what can happen is, like, though the variations doesn't exist in real life, you could actually see a significant jump because of a pixel being noisy. So this window function essentially helps us reduce the noise. So in a general world, we can use the window function like an average filter or something like a Gaussian smoothing filter. You can think of this as from the Fourier episode. The Gaussian filter basically is a Gaussian blur kernel, and the box filter is basically again another like averaging kernel, which again smooths out, but has different kinds of artifacts, but it's simpler to implement. Great. So this the first term is the shifted intensity, which essentially is like the pixel which is like neighboring pixel, which is what we picked, and the other one is where we are centered around. This is equivalent to the sum of squared distances between the point and the neighboring point, which essentially is giving us the gradient. Awesome. Let's continue building this concept. Let's call this the measure E, which is like with shift of U and V. And what we want to do is we want to come up with a matrix which essentially has the changes in X, the changes in Y, and the changes which are cross-coupled between X and Y. Using a first order Taylor series approximation for the term E, what we can do is we can say it can be written in a bilinear form like this. Beautiful. So bilinear form is great because we can do cool mathematical tricks with it, and it can become very efficient based on how we actually handle this. Now let lambda 1 and lambda 2 be the eigenvalues of the matrix M, which is like the edge correlation matrix, right? Great. So what we want to do is now let's plot lambda 1 to lambda 2. Recall that the eigenvalues relate to the spread of data. If that is not intuitive, I have a future video coming up just on that topic. Stay tuned and hit the bell icon and subscribe to the channel and like this video, please. So now let's take this region wherein both the eigenvalues are small. I want you to pause the video for a second and think about what kind of a region in the previous example we took, the red points, the green points, the blue points, would this be? The answer is a flat region, because when they are both small, it means that like your variations in both x and y directions are actually small. And that happens when your data looks very similar as you move around, right? Which is a flat region. So we have this kind of region wherein we have lambda 1 very large and lambda 2 small. So this is an edge scenario where E varies a lot in one direction but not the other, and we have the exact opposite in the other direction of the edge. Great. Anywhere we have lambda 2 approximately equal and they're pretty large, E changes a lot in all directions, which means it's a good feature, which is like the mountaintop. Great. And just to give you an example, like the spread, what we were talking about, this is from an actual data point. Great. So what we were just talking about is how to find a corner. Now let's come up with a simple algorithm, which is called the Harris Corner Detector. Recall that the values of lambda 1 and lambda 2 matter. We are looking essentially for uniqueness in both directions when we move around. We can come up with a heuristic for cornerness, or call this the corner metric, which is this function called R, where we multiply the lambda 1, lambda 2 minus k into lambda 1 plus lambda 2 squared. Again, this is a heuristic. Remember, like we have made this cornerness metric up, where k is a number, which is a constant. So this looks for both absolute and relative scale value of the lambdas at the same time. And what we can do is, instead of actually physically computing the eigenvalues, which could be slow, we know that lambda 1 into lambda 2 is the determinant of the matrix, and lambda 1 plus lambda 2 is the trace of the matrix. The cool part is, for a 2 by 2 matrix, the determinant and trace are very easy to find. And this is exactly what OpenCV's cv2.corner Harris implements for you. So this above equation is the original Harris corner metric. So the question is, what is so cool about this? We don't have to explicitly ever compute eigenvalues. We can just compute the determinant and the trace of a 2 by 2 matrix, and it's very, very quick. And we can essentially say that, hey, this point is a corner if the value of R is greater than some threshold, or the cornerness is above threshold. And if you have taken an optimization class before, you would sort of like relate this to something called the condition number, which is basically the stability of the system or the signal to noise ratio. Beautiful. Let's take the Lena image from before, and if we apply this corner metric R on a small window, and this is what we would see. This is color coded in a way that red has high values and blue has low values. So if I overlay it, you will see that like we see like good amount of green, yellow, and orange on the parts which we expect to be nice little corners, as what we would intuitively call as corners. Great. This is awesome. But Gianbo Shi and Carlo Tomasi came up with an even better metric than this, which is more stable when you try to match across multiple different viewpoints. And just by changing the way you would threshold, you can essentially get a better feature. And the Shi-Tomasi's cornerness metric is essentially utilizing the minimum of the two eigenvalues, call it a corner if it's greater than some threshold. The reason this works better is because the smallest eigenvalue is what determines the amount of noise in the system, right? It's like vaguely again related to the eigen, when you take the eigen decomposition compared to the singular value, this is vaguely related to the condition number of the system, which is the signal to noise ratio. So you want to essentially look for the highest noise floor, which affects the smallest eigenvalue, which is what we're talking about here. Great. Harris Corner is great. It is still utilized quite a lot in the field of computer vision, even today in the era of deep learning, but it has a bunch of issues. So the threshold tau needs to be chosen manually, which could be hard in certain cases. This doesn't work very well, and it's pretty painful when you are like zooming in or zooming out, which means that if you're changing the scale of the image, the match just doesn't work that well, right? And also because we are using very simple literal raw pixel values, it does not work really well with large illumination changes. And it also does not work with large rotation changes. So we got the corner locations. Let's say we have images where Harris works well or the Shi-Tomasi corner detector works well. Now, this is the equivalent of knowing your home address, right? But that does not really tell you what kind of a home you live in, if I want to like look for similar homes, right? Which is essentially matching the feature. So what we want to do now is, let's look at the corner point here, and this is the center, and we want to look at a neighborhood around the image which essentially gives you a description of what it looks locally. So think about this as like knowing your home address, which is the green dot location there, and knowing the size of the rooms and kind of things in your home or the layout of your home, which helps somebody else describe how your home looks like, right? Great. So let's continue doing that. So one simple way is we can take all these rows and columns and like sort of raster it out and just like overlay it into a vertical vector and use the raw values. It's a very rudimentary method and it kind of works when the viewpoint changes are very low, but it's not really that great when you're trying to apply it on a real system, right? A slightly better way is to use the histogram, which is basically counting the number of occurrences of each intensity value. It kind of works again, but again this can also like lead to really bad matches. So what we will do instead is we will select every, let's say, fifth column and every fifth row. We are essentially subsampling the feature because we are trying to like reduce the dimension, because we don't really care about the subtle changes, we only care about the larger changes, and subsampling sort of gets you that. So this is the equivalent of not counting every single time tile in every single room. Rather say, oh, this is a room and there's a neighboring room, right? And that's what we're trying to do here. Now take all the values here, and what we want to do is we want to standardize this data. When you standardize this data, you essentially are like boosting the contrast and you're removing noise and bias, which makes it better. So we'll take this descriptor and we can match. And this is a very rudimentary, simple feature descriptor coupled to Harris, which you can use to build your own panorama matching system, or a stereo matching system. Remember that this descriptor has a lot of issues. It's very simple, very rudimentary, and in the next episode we will make this a lot better. This descriptor does not work with changes in rotation because we never talked about rotation. It does not work with large changes to viewpoint. It does not work well with changes to scale or zoom like we talked about before, and it does not work with super large changes to illumination. It kind of has a little bit of illumination invariance simply because of the normalization factor, but again, if you try to use this in a very hard practical system, this might not work well. Okay, so just to quickly recap, you should be able to say how we see depth with stereo, what is the similarity between stereoscopy and panorama stitching, why are corners good feature locations, how would you construct a simple feature descriptor. See you next time. Thank you. Take care. Bye-bye.